briefly introduce organic chemistry by discussing compounds considered to be organic molecules and some important ideas including drawing organic molecules, functional groups, and structural isomerism. Organic compounds were originally thought to be compounds that can only be made in living organisms. The breakthrough was made by Frederick Wöhler, who discovered that he's able to synthesize urea, an organic compound, in his laboratory. This gave rise to the now multi-billion-dollar industry of synthetic organic compounds for industrial, medical, and other uses. Nowadays, organic compounds don't necessarily have to originate from living things. They are more broadly defined as compounds consisting mostly of carbon, hydrogen, and a smaller number of other elements. In this video and class, I will only discuss oxygen and nitrogen as those other elements, even though organic compounds contain a lot more of the other elements as well. We would start with organic compounds by discussing the simplest possible type, which is a hydrocarbon called alkanes. These compounds contain only carbon and hydrogen, and the carbons are connected to each other by carbon-carbon single bonds. Here you see the Lewis structure of the first three alkanes: methane with one carbon, ethane with two carbons, and propane with three carbons. You can see both the ball and stick model as well as the space-filling model here of these three alkanes, with carbon atoms colored black and hydrogen as white. The naming system of organic compounds is different than the one we use for inorganic compounds. Although we won't go in depth here, I'll briefly mention that there are specific prefixes used based on the number of carbon atoms that are present. For one carbon, we use meth, for two carbons, eth, and so on. To complete the name, we use a suffix that corresponds to the functional group of the organic compound. Organic molecules are large enough that part of the molecule serves as a structural component, meaning that they provide support, while a smaller part of the molecule serves a functional role, meaning that it actually participates in bond formation and breaking that occurs in a chemical reaction. The parts that serve a functional role is what we call a functional group, and we'll talk more about these functional groups later. Alkane is the simplest possible functional group, so if we want to name an alkane, we would just count the carbon atoms and end the name with the letters A and E. For example, a 1-carbon alkane is called methane, a 2-carbon alkane is called ethane, and a 3-carbon alkane is called propane, and so on. Because of their size, organic molecules are not as easily drawn as a complete Lewis structure as inorganic compounds. There are other ways to represent organic compounds without having to always draw the whole Lewis structure. Here on the left is a molecule drawn as a standard Lewis structure with all the bonds and atoms illustrated. Right next to it is what we call a condensed structural formula. Here, all the hydrogens bonded to a given carbon atom is represented as a group called CH with a subscript, where the subscript represents the number of hydrogen. For example, the one on the left is a CH3 because there is one carbon with 3 hydrogens connected to it. Right next to it is just CH because there's a carbon with 1 hydrogen attached to it. We draw lines between the CHN groups to represent the carbon-carbon bond. An even simpler representation is the line structure. Here, each of the CHN group is represented as a point, and only the carbon-carbon bonds are drawn. The same molecule now looks like this when drawn as a line structure, and if you're an organic chemist, you can quickly visualize the three-dimensional structure of that molecule based on the line structure. So there's a number of important functional groups in organic chemistry, and they're listed here in this table with the key molecular features that distinguishes that specific functional group. Now I'm going to discuss some, but not all the groups here as a way to introduce you to the diversity of functional groups in organic chemistry. The goal in general chemistry is mainly to recognize the molecular features of these functional groups. When you take organic chemistry courses, each of these groups will be the topic of study, including the reactions and the properties of molecules that contain these functional groups. Now, as we already said, alkane is the basic functional group, which is just the CC single bond. The single bond is less reactive than other hydrocarbons, although they do contain a lot of energy, which can be released if you were to burn or combust alkane. Now, there are two additional hydrocarbons hydrocarbon groups which are more reactive than alkanes. These are alkenes, which has a carbon-carbon double bond, and alkynes, which has a carbon-carbon triple bond. Now, both of these are what we call unsaturated hydrocarbons, meaning that not all the electrons are used in bonding with hydrogen atoms. In contrast, alkanes is what we call a saturated hydrocarbon. There's a plastic that's called PVC, or polyvinyl chloride, which is used in making everything from water pipes to credit cards. PVC is a polymer of an alkene. One of the most well-known alkynes is acetylene, which is a gas that we use in welding. Now, other examples of alkynes can also be used as starting materials for the synthesis of plastics. The last type of hydrocarbon is a different one than the other three because this is a ring hydrocarbon. So it's called arene, and arene is what we used to call aromatic hydrocarbons. The term aromatic comes about because these compounds were originally discovered in substances such as cinnamon bark, mint leaves, and vanilla beans, which have very strong and pleasant smells. The identifying group of an arene is the benzene ring, which you may recall was discussed in a video where I talk about the combination of valence bond and molecular orbitals. The benzene ring itself contains 6 carbon-carbon sigma bonds, as well as a pi molecular orbital, which allows the delocalization or spreading of the p valence electrons. This delocalization helps contribute to the stability of arenes. Now, the next set of functional groups that I'm going to talk about all contain oxygen atoms. The first one I want to talk about is alcohol, which contains the OH group, which is also called the hydroxy group, that is bonded to a carbon chain. Carbon chain is just a chain of alkanes. The most famous example of this group is probably ethanol or ethyl alcohol, which is the alcohol that can be used as fuel, but it's also the alcohol that you drink in beverages like beer and wine. You may notice that the OH group is capable of making hydrogen bonds, which result in the higher boiling points of alcohols compared to other organic compounds of similar size. The next functional group is ether, which is a class of organic compounds that contain an oxygen between 2 carbon chains, which we call alkyl groups. They are used in the manufacture of dye, perfumes, and essential oils. Ethers are relatively unreactive compared to other functional groups and are often used as solvents. The next 2 functional groups are related to each other, aldehyde and ketones. They both have a carbon double bonded to oxygen, which we call a carbonyl group. The difference is that the carbonyl in aldehyde is located at the end of the molecule, while the one in ketone is in the middle of the molecule. The carbonyl group itself is polar, so that determines the reactivity of this group of compounds. Aldehyde and ketones are found in many naturally occurring compounds, including spearmint oil, camphor, and vanillin from vanilla bean and jasmine. They're also important metabolic products in the cell. For example, when we drink ethanol, it's first metabolized into a toxic intermediate in the liver called acetaldehyde, which is a compound that belongs in the aldehyde group. Ketones are produced in the cell as byproducts of fat metabolism and can be detected on the breaths of people who are on low-carb diets. The next group is called carboxylic acid, which contains 2 oxygen atoms. The group is also formed from 2 functional groups that we mentioned before, the carbonyl, which is the C double bond O, and the hydroxy, which is the OH group. We often abbreviate both of these groups as one group called the carboxyl group, which is COOH or CO2H. The presence of these 2 polar groups result in strong intermolecular forces, at least compared to the other organic compounds, that makes carboxylic acid boil at higher temperatures. They're weakly acidic, as the name suggests, with the H in the hydroxy group being the one dissociated in water. They represent compounds as diverse as acetic acid, which you can find in vinegar, all the way to the fatty acids that you find in vegetable oils. The last group that contains oxygen that I want to talk about is esters. They look very similar to carboxylic acid, except that instead of an H after that second oxygen, it's bonded instead to a carbon chain. Esters are derived from carboxylic acid, and they're often found in food ingredients and also in animal and vegetable fats. The term saturated fats actually refer to esters that contain only saturated alkanes, while unsaturated fats are esters that contain carbon-carbon double bonds. These molecules are important in health because the saturated fats typically have higher melting points, which means that they can form solids solids in the blood vessels, which result in high blood pressure and other medical ailments. The last two groups that I'm going to talk about both contain nitrogen atoms. One is called amines, which are derivatives of ammonia, or NH3. Now, because ammonia itself is a weak base, these amine compounds are also bases. One of the most common amines that you may know is trimethylamine, which gives fish and other seafood its pungent smell. Now, you may know that we typically squirt lemon or lime on seafood to enhance its taste. The reason is that those citrus fruits actually contain carboxylic acids, which through an acid-base reaction can neutralize the base in the trimethylamine, forming salts. So this treatment not only removes the smell, but also it improves the taste of the seafood. Now, the last group that we're going to look at is called amide. It has both the nitrogen and the oxygen atom, and there's a variety of materials that are composed by amide, ranging from Kevlar, which is used in body armor, to caffeine in tea and coffee, all the way to the antibiotic penicillin. So the most famous example of compounds that contains amide is probably all the proteins that you find in humans, animals, and plants. These all use the amide bond as a structural component.
Now let's take a look at an example on identifying functional groups, all the ones that we just discussed in the lecture. So we have 6 different organic compounds, and they're given in a mixture of line structure as well as condensed formulas. So we just want to see what kind of functional groups we have. If we look at molecule A, the only functional group we have is the arene or the aromatic functional group, and there's nothing else. Now you might say that there's alkane as well there, but alkane is not considered a separate functional group. It's just something that exists in all organic compounds. If you look at the second one, in B, we have a few there. We have this one right here, which is your carboxylic acid. We have the arene again, or the aromatic. And then we have the COO with a chain on both sides. And so that, of course, is our ester functional group. We look at C, we have the aromatic again, or the arene. And then we have the OH group, which remember is the alcohol group. And then we have the N containing group, which is the amine here. And then for the D, we have our ring, but the ring here is not your benzene ring, which has a circle in the middle. So you don't want to say arene there. But you do have a double bond between carbon and carbon, so that corresponds to an alkene. You also have a C double bond O that goes to 2 other chain, so that's your ketone functional group, and that's pretty much it. Now, if you take organic chemistry, you also see that that one has a name. The halogen that's connected to a alkane, it's called a haloalkane, but we're not going to discuss that in this class. And in E, we see that we have, again, that component, but we're going to skip that one. And then we see we have our arene again, or aromatic. Now we have our N here in the middle that's connected to 3 different carbons. And so that's our amine. And then we have, in this case, a carbon. Remember that in the functional group line structure, this is a carbon that's double bonded to an O. There's no bond here, which means that it's just to an H. So that functional group, remember, is an aldehyde. So we have that. Now in the F molecule, we see that we have aromatic again. We have an alkene here, double bond right there. And then we also have an aldehyde. Now here, the H is actually highlighted and it's shown, unlike the previous molecule where the H is not shown. But either way, you should be able to interpret that correctly. So aldehyde is the last functional group in that molecule.